If you have a sibling, dodging paper airplanes is a likelihood. So what allows this plane to glide through the air and always seem to hit the back of my head? Well, it's not my brother's expert skills. It's lift. The simplistic way to explain lift is through air displacement. A wing pushes air above and beneath it downward, either through its curvature or angle of attack. This push creates downward momentum on the air, and according to the conservation of momentum, there must be an upwards momentum against the wing to counteract it. This explanation might be different than what you've learned in school, as the reasoning of lift is still widely debated today with many theories. Some textbooks explain that when air flows around a wing, the unique curvature makes the air flowing on top of the wing cover a greater distance than the air beneath the wing. As the distance is greater, this means the velocity of the air flowing above the wing must be faster, so the air flows can meet simultaneously at the trailing edge. These differences in velocity can then affect lift force through Bernoulli's equations, which explains that when velocity is higher, pressure must be lower and vice versa. This creates an area of lower pressure above the wing and an area of higher pressure beneath the wing, creating a pressure difference which supplies an upward lift adhering to the conservation of energy. So let's look back at our paper airplane. Since our paper is completely flat, the air flowing on the top of the wing doesn't travel a greater distance than the air beneath, so theoretically, no lift would be generated. But our airplane still flies, disproving this equal transit time explanation. In fact, there's no law of physics which states that the air must meet simultaneously at the trailing edge, and subsequent studies have shown that the air across the top moves so much faster that it ironically reaches the trailing edge long before the air beneath. Though the equal transit time explanation is wrong, there is a pressure difference between the top and bottom of a wing. The reason for this pressure difference can still be explained by the Bernoulli equations, but also through ideas like streamline curvature. In the end, both of these explanations hold some truth, and it requires components of each to accurately adhere to the laws of conservation. So, if there are so many explanations for lift and nobody quite agrees on what model, how can we confidently create the miracle which are airplanes? Well, fret not, my flight-fearing friends. The engineers know exactly what they're doing. Through the Navier-Stokes equations, engineers and aerodynamicists can undisputedly calculate exactly how air flows around a wing. These equations work to completely account for the conservation of mass, momentum, and energy when it comes to lift. In a sense, this is the equivalent of your parents saying, well, it's this way because I told you so. So even though the explanation of lift is still widely debated,
let's go!
It's clearly still happening.